In the last lecture, we defined our two-dimensional Markov Lie algebra basis in terms of L12, which was this matrix, and L21, which was this matrix. The commutation rules were given by this, and we pointed out that this was the lowest order Lie algebra that exists. And in fact, every order 2 Lie algebra is equivalent to this Lie algebra, which we're going to be referring to as the Markov Lie algebra in 2 dimensions. We've verified that this was a Markov transformation, and we expanded M as e to the epsilon times one of these, which would be L12, although this, a similar theorem would hold for the other one. We continue now by saying by iteration of that infinitesimal transformation, one obtains a Markov transformation in general, which is going to be e to one parameter lambda12 times L12 plus another parameter lambda21 times L21. And that will give us, since this is the most general element of the Lie algebra, the Markov Lie algebra, this will give us the most general element of the Markov Lie group. And this, in fact, will give us all Markov transformations that are continuously connected to the identity, at least in 2 dimensions. And specifically, we need to work this out. So let's take the first one of these and see what kind of transformation this gives when it's in a finite form. E to the lambda12 times L12 can be expanded, and one quickly verifies, and this is easily done in just a few minutes, that when you do this expansion, you get 1 and 0, and e to the minus epsilon in this position, and 1 minus e to the minus epsilon, lambda, in this position. Likewise, e to the lambda21, L21, will give us this in terms of the other lambda. I should have labeled that as lambda12, and this is lambda21. Again, it's very easy to check that if I add up these, I get a 1 here. If I add these two, I also get 1. Therefore, it's a Markov transformation. And in general, one can see that if I take either of those transformations, multiply back to the left on a 1, that is equivalent to summing over the rows for a given column, and that is invariant. And now here is the tricky part. One verifies that if and only if the lambda is greater than or equal to 0, then the m's are all positive, non-negative. Now we can see that because if lambda could become negative here, this term right here would be e to the lambda. And e to the lambda is going to be greater than 1, and so 1 minus e to the lambda would be negative. Therefore, this works exactly for and only for lambdas that are non-negative. That will be the key to what we have done, is in choosing a really good basis for this Lie algebra so that the parts that are in violation of what we expect in a Markov process will be easily eliminated as the numbers or coefficients in the Lie algebra that are in fact negative. I now want to move on for a moment to what we call the general linear group, or the general linear group in n dimensions over the reals. This gives, in fact, the dimensionality. It means these are n by n matrix transformations that are, and since this is a Lie group, continuously connected to the identity with only real parameters. These are all of the non-singular, that is, invertible linear transformations in n dimensions that continuously connect to the identity. It's obvious that there are 2 other linearly independent matrices in 2 dimensions different from the ones we've just discussed, L12 and L21. Namely, if we look at an object that I call L11, which is equal to 1, 0, 0, 0, and another object L22, and these are named because they have a 1, a plus 1 in that particular location, as 0, 0, 0, 1, then these two transformations, L11 and L22, along with L12 and L21, obviously form a basis of all the 2 by 2 matrices. And therefore, they form a basis of the general linear group in 2 dimensions over the reals. We can form that by taking e to the lambda 11 times L11 plus lambda 22, L22, and so forth. There are therefore obviously 4 independent matrices in 2 dimensions because it's 2 by 2. And 4 independent parameters will give us all continuous evolution away from the identity. And that gives us our general linear group in 2 dimensions. Let's look at what these other 2 transformations are. Obviously, e to the lambda 11 L11 can be re-expressed in this form right here. And likewise, e to the lambda 22 L22, this right here. These transformations are what we call scaling transformations, in that they represent exponential growth or decay depending upon whether lambda is greater than 0 or less than 0 respectively. If lambda is greater than 0, then of course this becomes greater. It just means that this axis is expanded and all of the values are expanded in that direction while the other axis is left alone. Or here, this axis is expanded. If lambda is negative, then in fact this becomes reduced or shrunk, and so we have a decay rather than an exponential growth. Thus, the general linear group in n dimensions over the reals can be decomposed here into 2 types of transformations. Scaling transformations, which is an abelian subgroup. Naturally, these commute with each other, so it's an abelian group of order 2. And 2 Markov transformations, which is the lowest non-abelian group of order 2 that one can have, as we will show later. Let's return now to our Markov group and the general linear group at a higher order of dimensionality than 2. Now, from general observations, one could see that we could do this in n dimensions without any trouble. Our Markov transformations would have the form Lij, where we put a 1 in the ijth position, and that defines this matrix. We would then put a -1 directly below it, because we must have this matrix such that it sums to 0, because when we expand the exponential, and be careful with this, listen, when we expand the exponential's first term is 1, 1, 1, 1, which looks like the identity. And since the sum of the rows for any column is already 1, it follows that every other element in the expansion of this transformation must have the sum over all rows equal to 0. So we could define a 1 in any arbitrary position, zeros everywhere else in the transformation, and a -1 on the diagonal here. And that will be the basis for this element of the Lie algebra in n dimensions. And again, I point out here that's necessary because if we write e to the epsilon times L, we get 1 plus epsilon L. And since the sum over this 1, this is 1, 1, 1, 1, 1 on the diagonal, the sum over that for all columns in any for any one column and all rows is going to be 1. This sum must be 0. Well, this accomplishes it, because any parameter I multiply here, I'll get that parameter and minus that parameter, and so those sum to 0. And so this is going to work. Now, we can use the expression, and we will, Markov group in n dimensions over the reals for the Markov type Lie group in n dimensions. We will see that the Markov Lie algebra has n squared minus n, or n times n minus 1, independent elements of the form given above. Why is that? That's because we can put a 1 independently at any one of the off-diagonal positions. Now, the total number of positions of an n by n matrix is n times n, or n squared. So we've got n squared possible places to put it, but we can't put it on the diagonal. So that's n squared minus n, and that's where we get this term here, or n times n minus 1. The rest of those n transformations to make up n squared linearly independent matrices come from putting a 1 along the diagonal, and these are the n diagonal scaling transformations. If I then take all of those matrices, I can form the general linear group in n dimensions over the reals, not just 2 dimensions. Let's look at some of the properties of this Markov type Lie algebra, MNR, the Markov Lie algebra in n dimensions over the reals. The first thing I want to look at is a transformation which is an equal mixture of the two parameters, e to the lambda L12 plus that same lambda times L21. Now if you form that matrix and expand it exponentially, it's a little bit messy, but within a few minutes you can reduce it down to the form 1/2 of 1 plus epsilon to the minus 2 lambda, 1 plus epsilon to the minus 2 lambda, and the off diagonal is 1 minus e to the power 2 lambda. 1 minus e to the power 2 lambda. I meant to say e a minute ago instead of epsilon. Now, as we let lambda approach infinity, in other words, we let that evolve as though it's a parameter with time, where we evolve this transformation and act again and again and again and again, we can see that as lambda approaches infinity, that here we get for each of these exponentials, e to the minus infinity, or 1 over e to the infinity, which is 0, leaving us with a transformation 1, 1, 1, 1. Multiplied by the 1/2, this gives us a 1/2, 1/2, 1/2, 1/2. Now that transformation is really like a diffusion, in that we have moved forward from whatever state we might have, x and y, that this thing is acting upon, and whatever state we started with is totally obliterated in the distant future, because we have diffused into one common equilibrium state from any other state. And from one point of view, and this is perhaps the most trivial thing I can say, and maybe the most important at the same time, we have lost the information of what the state was really like. We can say that the entropy has continuously increased. Now, why would we say something like that? Well, we could imagine that we start out with a state, x and y, and if x was equal to 1 and y was equal to 0, we would say, oh, we understand that the vector is pointing upward. Or like with the spin of a particle, if we start out with 0, 1, it means that the probability of spinning down or being false is certainty. By acting with this transformation on those two vectors, or any other transformation, we end up in the very distant future with vectors that are equal mixtures. So the knowledge of whether a particle was spinning up or spinning down has been totally obliterated. We end up with mixtures of equal spinning up and equal spinning down, which means that we have no information at all. And that's why I make the statement that the entropy has continuously increased in a gradual process of losing information. Well, that is the reason that I feel that there's great importance to be placed on these types of transformations in the study of this group, because we will see as we move along, this type of transformation is very closely linked to both diffusion and therefore to entropy, and consequently to the concept of information itself. Now, going to the second point, if we look at what is called the killing form, which is the metric Gij, which can be formed from the structure constants by contraction over the k and contraction over L's for any given I and j. And of course this is an equation that one should remember as being very important in Lie group theory and Lie algebras, is formed totally from the structure constants And by summing over this index and summing over this index, we end up with what would be a totally symmetric form, because obviously if I interchange these, I get the same answer. One obtains a matrix for that, which is the matrix 1, 1, 1, 1, from the structure constants that are associated with this Lie algebra. A Lie algebra, you will recall, is semi-simple if and only if G is not equal to 0. Therefore, it follows that this algebra is not semi-simple. So we have found something very interesting here. The Markov algebra is not semi-simple, and therefore it is not a member of any one of the 4 primary series of Lie algebras that are semi-simple, nor is it one of the exceptional Lie algebras. Looking at the next property, 3, we can define L as L12 minus L21 and look at the commutator, and we can see that L times L12 is equal to L, which is also equal to the commutator of L, and I believe this is, yeah, that's correct, with L21. Therefore, L forms an invariant subalgebra, or ideal, and therefore the algebra is not only not semi-simple, it's not simple, because it has an invariant subalgebra. Property number 4 is the algebra is also non-compact. It's non-compact since the parameter space is unbounded. Another example of an algebra that is unbounded that we have studied is the Lorentz algebra, and that is because we can go effectively with a transformation that is faster and faster and faster and faster without limit. Although it's non-compact because in that case it does not have the limit point, which is a transformation with the velocity of the speed of light. On the other hand, if we look at the Lie algebra for the orthogonal transformations, or the rotation group, the rotation group is compact. And we do not have an infinite number of transformations because of the modularity of rotating about by a given angle. We get back to where we started from again. The 5th property I want to look at here is that the Markov group in n dimensions over the reals gives us motion on a hyperplane that's perpendicular to this vector 1, 1, 1, 1, 1, which we write as bra vector with a 1 in it, and this is an invariant vector. Now, since that vector is invariant, and we know it is because we proved that m acting to the left on that bra vector is invariant, and therefore the transposition of that equation, transpose of that equation would give us the same invariance. It follows that these transformations are moving us around on the plane that is perpendicular to that value. So if you imagine this vector which points out into, in 3 dimensions it would look like this, pointing out into space with the components 1, 1, 1, 1, 1, 1, 1, 1. In other words, it has the equal component along each of the axes, and it points directly out in the center of the positive hyperquadrant in n dimensions. Then in fact it follows that transformations must not shift me along that axis, therefore can only move me in the surface that's perpendicular to that vector, which is the hyperplane that intercepts all of those axes at the same value. Continuing with more properties of the Markov type Lie algebra, we next want to look at the Casimir operators. Now it turns out that the Casimir operators in generally are defined in the Lie algebra by the following expression. And we've written an I over here to mean we have an invariant of order n. This is a complicated looking expression, but it's important because I don't believe we've used this expression before to understand the terms. we have a whole set of products of the structure constants, and we have a whole set of products of the L's. And this only starts when we have at least two L's, and these are labeled as L with an alpha 1, alpha 2, up to an alpha n. So they're going to be n of these. Therefore, this object that we're forming is not actually in the Lie algebra. The Casimir operator isn't. It is rather in what is called the enveloping algebra, namely the algebra that consists of all possible products of the matrix representations, i.e. the representation space of this Lie algebra. Only there can we form a product of two types of matrices. In a Lie algebra, we cannot do that. We can only multiply a matrix by a number and take the commutator of two matrices. We can't multiply two of them as products. However, once we find a representation space, we can take the product, because then we're just multiplying one matrix by another matrix. That algebra, again, I mentioned, is called the enveloping algebra, the algebra of all possible products. Therefore, what we're looking at here is something that's nonlinear. The Casimir operators are not linear. You will recall that j squared is jx squared plus jy squared plus jz squared. The way that we form this invariant is we take the summation over this index, beta 1, with this beta 1 here, this beta 2 with this beta 2 here, until we have here a C with a beta n minus 1, and it contracts with beta n minus 1 up here. The beta n, which is left here, contracts back in a circular fashion to the beta n that is the index for the first one of these transformations. That means that all of the upper betas and all of the lower betas are exactly summed over. And this expression consists, therefore, of only indices that are free, alpha 1, alpha 2, up to alpha n, which is contracted with these, and that gives us a very, very complicated set of products that are not linear of the various L's that are in the Lie algebra. Now, these elements can be shown in general and for Lie algebra theory to commute with all of the L's. They may not all be independent. For example, if we went on and used not only j squared but other types of j's that were higher powered, we would not find that there were more invariants in the rotation group. We'll continue this in the next lecture.